Today's topic is regarding multiple linear regression analysis. Okay, so multiple linear regression analysis is an extension of simple linear regression analysis. Okay, so you need to recall our previous lecture regarding simple linear regression analysis. Okay, so let us proceed with our topic. Okay, so the objective of this lecture is to introduce regarding the concept of model building in multiple linear regression, and also how to perform multiple linear regression analysis in SPSS. Okay, you can perform this analysis using other software as well. For example, you can use R, you can use Stata, and you can use other software as well. But since we are more familiar with SPSS, and we think that the output of SPSS is easier to understand than for beginners, then I think showing how to perform analysis in SPSS is easier compared to using other software. Okay, so what is multiple linear regression analysis? It is an extension of simple linear. It is a type of multivariable univariate analysis. Okay, so what does it mean by multivariable? Multivariable means that you have more than one independent variable. And univariate analysis means that you have one dependent variable. Okay, so now you have more than one independent variable. You are going to predict one dependent variable. Okay, so linear regression concern with a numerical dependent variable. So your outcome variable must be numerical. Okay, so the aim of linear regression is to estimate linear relationship between a dependent variable and more than one independent variable, or for numerical variable, you can call it covariates. Okay, so now you are studying more than one independent variable. Okay, so you are studying more than one independent variable, the influence of more than one independent variable towards an outcome variable. And the outcome variable must be numerical. Okay, for example, if you do a simple linear regression, you are looking at the influence of one variable towards an outcome variable. Okay, so this analysis, we call it a simple linear regression analysis. Okay, and it is usually inadequate to do a prediction of an independent variable based on just one independent variable. Okay, because in real life, there will be more than one variable which can influence the outcome variable. Okay, so for example here, what can influence cardiorespiratory fitness? For example, age, body mass index, and also blood pressure. Okay, but you can include other factors as well. Okay. So doing a simple linear regression, it is just looking at the effect, the association between each independent variable towards the outcome variable separately. Okay, so now here, for example, you perform three simple linear regression. So the first simple linear regression, you are looking at the association between age toward cardiorespiratory fitness. Okay, then you perform another simple linear regression looking at the influence of BMI towards cardiorespiratory fitness, and the third linear regression, you perform analysis looking at the influence of blood pressure towards cardiorespiratory fitness. Okay, so now when you perform three simple linear regression analysis separately, you are looking at the association separately. Okay, so in real life, we cannot look at the association separately. We need to look at the influence of all independent variables simultaneously towards the outcome variable. Okay, so by using multiple linear regression, relationship between the predictors and the outcome variable can be examined concurrently, and it allows assessment of association between predictor and outcome variable while considering the effects of other predictors. Okay, for example, here you can see the influence of age towards cardiorespiratory fitness when BMI and also blood pressure are adjusted. Okay. So the predictor variable may be related to each other through confounding effect and also interaction effect. Okay, they might have confounding and also interaction between all these three independent variables. Okay, so confounding effect. BMI cannot be said to solely associated with cardiorespiratory fitness, as aging also can lead to reduced physical activity, resulting in an increase in BMI. Okay, it means that aging causes increase in BMI, and these two effect, confounding effect, does influence cardiorespiratory fitness. Okay, so it means that the relationship between BMI and also cardiorespiratory fitness is confounded by age. So by looking at the association separately, for example, BMI, by looking at the association between BMI and cardiorespiratory fitness separately, age and also blood pressure is unadjusted. Okay, so doing simple linear regression analysis, you cannot adjust for other variables. So the aim of multiple linear regression is for adjustment. So for example, in this model with three independent variables, you can examine the effect of BMI towards cardiorespiratory fitness while adjusting age and also blood pressure. Okay, you can also look at the influence of age towards CRF while adjusting for BMI and also blood pressure. And also you can examine the effect of blood pressure towards CRF while adjusting for age and also BMI. Okay, so regarding interaction, so for example, regarding interaction, you have two independent variables, muscle strength and also flexibility, and the outcome variable is cardiorespiratory fitness. Okay, when muscle strength increase, flexibility does not increase, CRF increase by 1 unit, we call it muscle strength effect only. Okay, the effect of only this one variable. Okay, the outcome variable increase 1 unit with increase in 1 unit of flexibility, so we call it flexibility effect, this variable effect. When the two variable increase 1 unit each and the outcome variable increase by 2 unit, we just plus these two variable changes, we call it combined effect with no interaction. Okay. However, if the two variable increase by 1 unit and the outcome variable increase more than what we expect, okay, then we call it, this condition is an interaction. Okay, so for this one we call it combined effect with synergistic interaction. Whereas when the independent variable increase 1 unit each and the amount of increase in the outcome variable is not as much as we expect, then it is also called an interaction effect, antagonistic interaction. Okay, so by doing multiple linear regression, we can examine interaction and also confounding effect. Okay, so multiple linear regression is an extension of simple linear regression. So you remember simple linear regression, the equation is y equal to beta 0 plus beta 1x. So beta 0 is the intercept, beta 1 is the slope. Okay, so x is one independent variable, the value of the independent variable. Whereas in multiple linear regression analysis, the equation is the equation of simple linear regression plus the equation for other variable as well. Okay? So for example here, if we have n independent variable, so beta 2 is the coefficient slope for the second independent variable, beta 3 is the slope for third independent variable, and so on. Okay.
Okay, Doctor. Hello, doctor.
If you have any question, you can ask me anytime. Okay, any question?
Doctor, about the antagonistic interaction, what do you do if there's an antagonistic interaction? Do you remove one of the variable or?
During analysis, you can examine the interaction effect. Okay, we will examine the multicollinearity and also interaction effect. If there is an interaction effect, you need to report it in your analysis. Okay.
Okay.
I have
Later,
another.
I will show you how to perform testing for multicollinearity and also testing for interaction. Okay, yes, another question.
Yes, hi doctor. So
Right.
based on the previous table, what do you mean by flexibility?
Flexibility, it is the measure of flexibility of a person. Muscle strength and also flexibility.
It's an example. It's an example.
Yeah.
Sorry, what?
Flexibility is a measure of flexibility of a person, lah. Right? When you measure a person fitness level, right? One of the component of fitness is flexibility.
Okay, so which means there are different parameters. So, does it mean that there are parameters that exist that do not have flexibility?
No, this is just
Or,
an example of two variable for prediction of.
okay. All right, got it. Thank you.
Okay, so any other question? Okay, so if not, then let's proceed. Okay, so again, this is equation for multiple linear regression. Okay, so again, as with simple linear regression, the importance of each independent variable on the outcome variable, it depends on the regression coefficient, the slope, right, the beta, the 95% CI of the beta and also the p-value, right? Okay, so these are the steps to perform multiple linear regression analysis. Okay, as with other analysis, we begin with data exploration. Then we perform simple linear regression analysis. Okay, so simple linear regression analysis, how to perform? It is just like our previous lecture, what I've shown you in the previous lecture. Okay, the next one is variable selection. Right, we do variable selection to obtain a preliminary main effect model. We check the model fitness, then we check multicollinearity and interaction effect. Right, then we check the model assumption, and lastly we do interpretation and also presentation of results. Okay, so for example, a researcher would like to determine association between age, BMI, systolic blood pressure, diastolic blood pressure, body fat percentage, and resting heart rate with cardiorespiratory fitness level measured by maximal oxygen uptake capacity, VO2 max. Okay, so the equation, the preliminary equation is like this. Okay, VO2 max equal to A, the intercept, plus beta 1 H plus beta 2 BMI plus beta 3 SBP plus beta 4 DBP and also plus beta 5 body fat percentage and also beta 6 resting heart rate, right? So we have 6 independent variable to test whether these 6 independent variable have any association with VO2 max. Okay, so let's open the data set. Okay, so this is the data set. So the independent variable is which one is the independent variable? VO2 max is the outcome variable. Okay, so now we are looking at the association between Share. Okay, so this is the data set. So the aim is to look at the association between these 6 independent variables towards VO2 max. Okay, age, BMI, SBP, DBP, body fat percentage, and also resting heart rate. Okay, so the first step is to do data exploration. Right, so data exploration, the aim of data exploration to look at missing data, distribution, and also outliers. Okay. The main aim in data exploration is to see whether there's, of course, missing data. What we can do with missing data, we can do, for example, data imputation. Okay. If you don't want to do imputation, then the software will do listwise deletion, right? So it means that when you have missing data, the observation will be listwise deleted. Okay, we call it listwise deletion, right? And also, we want to examine the distribution in order to identify outliers which are due to error in data entry or error in measurement, measurement error. So those things need to be corrected before you perform analysis. Okay. Okay, so for example, let's perform this analysis. Data exploration. Okay, we do data exploration by using explore function. Okay, for example, age, what else? BMI, SPP, DBP. BMI, SPP, DBP. Okay, and you can also examine the dependent variable as well. Okay, because now we are going to explore all these variables to look at missing data and also the distribution, and also whether there's any outliers to identify if there's any error in data entry. Okay. So under plot, I always take histogram and also normality plot with test. Continue and then okay. Okay, so the first table, case processing summary, will show you whether there's any missing data or not. Right? Then the descriptive table, this one to examine the distribution of each numerical variable. Okay, for example, age of participant, you can quantitatively determine the distribution by looking the mean and the medians, the standard deviation in relation to the mean, okay, the skewness and kurtosis values. Okay, so you need to examine all these quantitative parameter to assess normality, to assess distribution of each independent variable. Okay, the next table is test of normality. You can use Shapiro-Wilk test to determine distribution of each variables. Okay, you can look at the histogram for each variable, the QQ plot, and also the box and whisker plot. Okay. Okay, this step is actually an important step before you perform analysis. Okay, so just make sure you don't have any error in data entry and that there's the missing data is at minimum. Okay. Okay, so the next step. Okay, regarding data exploration. Any question?
Yes, when you say missing data is minimum, is there any minimum number allowable or it need to be zero?
Normally less than 5%.
Less than 5. Okay,
Normally less than
thank you.
5%. Okay. So in many discussion, when you have less than 5% missing data, you can do imputation of missing data. Okay, you can do imputation of missing data, but imputation of missing data is not part of our syllabus. But you can do imputation. If you have lots of missing data, it is not advisable to do imputation of missing data. Okay, so you need to, the software will do listwise deletion. So what happened, your final sample size will be much reduced than your initially required sample size due to that missing data. Okay? Okay, any other question regarding data exploration? So, for example, what happened if you have lots of missing data in one variable? Okay, for example, regarding body fat percentage, for example, body fat percentage 20% missing data, for example, what you are going to do? Okay, so if you have lots of missing data within one variable, you can exclude this variable from analysis. Okay, so don't include this variable in analysis. Okay, so let's proceed. Okay, so the next step is to perform simple linear regression analysis. Okay, we do simple linear regression analysis for each of the independent variable. Okay, we examine the influence of each independent variable towards the dependent variable separately. Okay, simple linear regression. Okay, so let's perform simple linear for the first independent variable, age. So for age, so again, similar step, like simple linear. So you go to analyze, regression, linear. The dependent variable is your outcome variable, VO2 max, and the first independent variable is age. Okay, under statistics, we select confidence interval 95% to obtain the 95% confidence interval. Okay, then just click continue and then just OK. Okay, so again, like simple linear regression analysis, what we are going to evaluate is the importance of this variable, the influence of this variable age towards VO2 max. So we examine the value of beta, unstandardized coefficient beta, okay, and also the p-value for beta. Okay, so here the unstandardized coefficient, the beta value is negative 0.229 and the p-value is 0.173. Okay, so at univariable analysis, we can see that as age increase, VO2 max reduce. Okay, how much reduction in VO2 max? By 1 year increase in age, VO2 max reduced by 0.229 unit, right? But the association is not significant, right? It is more than 0.05. So we can see here at univariable analysis, age is not an important predictor for VO2 max. Okay, so we can also examine the model fitness for age. The R square is 0.019. Okay, so what does it mean by 0.019? It means that age only explain 1.9% of the variation in VO2 max. Okay, so it means that age have very small influence towards VO2 max. Yeah? Okay, so when you do simple linear regression, you look at the coefficient table. The importance of each variable is determined by the beta value and the p value, right? But we are not going to make conclusion based on simple linear regression analysis. Okay, doing simple linear in multiple linear regression is just part of variable selection process. Okay, so we can relax the p-value, the cutoff point p-value for variable selection, right? Why? Because it is not necessary, this p-value not significant at univariable analysis. It is also not significant at multivariable analysis. When adjusted for other variables, this variable can be significant at multivariable analysis. Okay, so that's why usually we select the cutoff point of 0.25, okay, for variable selection, right? So we are doing simple linear regression just as part of the process of variable selection. So we are not going to conclude based on simple linear. So for candidates of variable to be included in multivariable model, so we normally choose 0.25, okay, for this p-value. Okay? Okay, then we repeat the process. We repeat the simple linear regression for all other variables, right? So for BMI, SB of all the univariable analysis. Okay, so for example, you can have this table as summary for simple linear regression, right? Okay, so regarding modeling of multiple lists, okay, there are several methods depend on researcher. If you think that you want to select few variables from all the list of all variables you collect, then you can perform variable selection, right? But for some people, they don't want to do variable selection. They purposely want to include all the variable in their multiple linear regression analysis, so they don't have to do this step, right? Okay. Step 3 is variable selection to obtain preliminary mean effect model. Okay, it means that you include only part of all these variable in your multivariable analysis. Okay, beginning with variable selection. Okay, so during variable selection, variable with p of less than 0.25 at univariable level and or clinically important should be included in variable selection. Okay, so it means that you can include variables with p of less than 0.25 or any other variables which you think it is important, right? So regardless of p-value, if you think that this variable need to be included in multivariable analysis, then you can include it as well, regardless of the p-value. Okay? Okay, so traditionally, we use automated method for variable selection, right? We usually use stepwise method, backward method, and also forward method. Okay. If you use automated method, all these three methods should be evaluated and should be compared. Right? You need to compare the result of these three methods. Okay. So this is one of the modeling option to develop model for linear regression. Yes, for some people, they don't want to use automated method. Okay, they want to use purposive method, right? So in purposive method, they manually enter whatever variables to be included in the model, right? Okay, when you use automated method, you choose model with the biggest number of significant predictors, the model which is biologically parsimony, which means that the simplest model that can explain the data is to be preferred, right? For example, when you perform stepwise, forward and also backward, For example, forward method retain 3 variable and backward method retain 4 variable, right? So you need to choose model which have the biggest number of significant predictor, and the model must be simplest model and also statistically sound based on p-value. What does it mean by simplest model? It means that the model need to contain variables which can be easily explained to others. Okay? Sometimes when you do modeling for regression analysis, by chance the model will retain some variables which is difficult to be explained. Right? So you cannot, by common sense, you cannot explain how does this variable influence the outcome variable. Okay, so you can purposely remove that variable from your model. Okay, so let's look at the first method, stepwise method. Okay, so now from our univariable analysis, let's say I want to do modeling based on p-value of simple linear regression, right? So I'm going to include these 4 variables, age, BMI, SBP, and also resting heart rate. Okay, again, recall the dialog for linear regression. So in my analysis, I'm going to include age, BMI, SBP, body mass index, SBP, and also resting heart rate. Okay, so I include all these 4 variables in my model. Okay. Again, under statistics, I ask for 95% confidence interval. Okay, to determine method, okay, we need to select this one, method, okay, either stepwise, forward or backward, right? So we begin with stepwise method, then click OK. Okay, we look at the coefficient table. Okay, we look at the coefficient table. In the stepwise method, we start with 1 variable. Okay, initially we intended to include 4 variables in our model, but stepwise regression begin with the first variable, right? We begin with the first variable, so the model is significant at the first step, the first model, okay? And it begin to add in another variable, okay? So for example here, it add in resting heart rate, okay? The second model in the stepwise method contain 2 variables, both are significant, okay? And it stopped at step 2, right? It stopped at model 2. So the software could not add in another variable. By adding another variable, the model become not significant. Okay, so it stopped with 2 variables, second model. Okay, so based on stepwise regression, only 2 variables significantly associated with VO2 max. Okay, so these 2 variables are important predictors for VO2 max with stepwise regression. Okay, so before doing conclusion, we need to compare this method with other methods. Okay, so again, you perform the analysis, you choose another methods backward, then click OK. Again, look at the coefficient table. Backward method start with full model. The first model contain all 4 variables. Okay, some significant, some not significant, right? Okay, so you begin by start removing the most non-significant variable, okay, systolic blood pressure. So if you see here, systolic blood pressure, the p-value is 0.85. So model number 2, it remove SBP from the model. So what happened? So you have 3 variables. Age of participant is not significant, so the subsequent model, age will be removed, right? So after removing age, so both variables significant, BMI and also resting heart rate. So this is backward method. So backward method and stepwise method it retains both these two variables, BMI and also resting heart rate. Okay, again, then we repeat this process for by using forward method. Forward method is more or less similar with stepwise regression. You start with empty model, then model number 1. It includes the first significant variable, BMI. Okay, the next one, resting heart rate included, right? So then it stops at model number 2. So by adding another variable, the variable become not significant. Okay, so it start with at model number 2. Okay, so similarly, forward method retain these two variables, BMI and also resting heart rate. Okay, so sometimes when you do modeling using automatic method, the number of variables retained at the end of the analysis, sometimes it is different using different method, right? So you need to evaluate which method retain the most number of variables, all variables significant, and it can be easily explained, right? Okay, so here you perform stepwise, backward, and also forward. Okay, so up to now, we have already obtained the so-called, we call it a preliminary main effect model, which consists of BMI and also resting heart rate as predictors for VO2 max. So at this point, our equation contain only two variables, right? So VO2 max equal to the intercept, 83.21. So where do we get it? From the coefficient table, the last model, the constant, 83.21. Okay. The first intercept, minus 0.77. Okay, so minus 0.77 times BMI and also minus 0.61 times resting heart rate. Okay, so this is the equation from the preliminary main effect model. Okay, so you can also check the model fitness. You need to check the model fitness comparing the three models. All right. So, for example, the stepwise, the R square is 73.1%. Okay, backward also 73.1%. Forward also 73.91%. Okay, so these three models, regardless of the method, either stepwise, forward, or backward method, the model fitness is actually similar. Okay. Okay. So any question so far regarding checking model fitness? Check the model fitness. Check and compare model fitness. Okay. So next step is to check multicollinearity and interaction. Right? Multicollinearity happens when the independent variables are highly correlated with each other. Okay. You can examine multicollinearity by using correlation metrics. And for example, in this data set, you can examine the correlation. Age, BMI, systolic, resting heart rate. Okay, you can examine the correlation metrics and look at the correlation between variables. Okay, so for example, if in your model you include age of participant and also body fat percentage. Okay. So in our model, we don't include BMI, age, and also body fat percentage. But if you include age and body fat percentage, the correlation between age and body fat percentage is high, right? Very strong correlation. right? Strong correlation between age and also body fat percentage. So these two variables are highly correlated with each other. So when you include both variable in the analysis, so you will have the problem of multicollinearity. Okay. So the cutoff point is actually arbitrary, but normally we use R of more than 0.75. Some people use more than 6 to say that the two variables are highly correlated. For example, another example, age with diastolic blood pressure, also highly correlated. Okay, BMI with body fat percentage, BMI with diastolic blood pressure, right? Systolic blood pressure and diastolic blood pressure, right? So actually, instead of uh, instead of using both variable, you can come up with another variable which can explain these two variables. Okay, for example, mean arterial pressure, MAP. MAP is can be calculated from systolic blood pressure and also diastolic blood pressure, and mean arterial pressure can represent both systolic and also diastolic blood pressure. Okay, body fat percentage correlated with age, BMI, and also systolic blood pressure, and also diastolic blood pressure, and also resting heart rate. Okay, so in fact, if your model contain body fat percentage, right, it can have high correlation with all other variables. Okay, this is one of the method to determine multicollinearity. Okay, but in multiple linear regression analysis, there's some formal way to check for multicollinearity. Okay, standard error of parameter estimate become very wide. Okay, you can have wide confidence interval for the coefficient, the beta, when you have multicollinearity issue. Okay, if you remove variable with multicollinearity, okay, the regression coefficient might change, and also sometimes there might be changes in the direction of regression equation by removing the highly correlated variable. Okay, so in SPSS, okay, you can use this option, collinearity diagnostics, to check for multicollinearity. So for example, if I run linear regression, okay, with only two variables in our preliminary mean effect model, BMI and also resting heart rate. Okay, under statistics, we take collinearity diagnostic, continue, and then OK. So in the coefficient table, you'll be given one collinearity statistics. Okay, collinearity statistics describe multicollinearity between these two variables. Okay, the cutoff point is the tolerance need to be more than 0.01, and the VIF need to be less than 10. Okay, VIF can be calculated from the tolerance. VIF is just 1 divided by tolerance. So you can look at any one of these two values, either one, right? So normally we just look at the VIF, easier. VIF need to be less than 10. Okay. So after variable selection, I forgot to mention, the method stepwise forward and backward is just to be used for variable selection. After that, you can use enter method. Okay. So enter method still same tolerance and also VIF. Okay, what happened if in our model we include body fat percentage and also blood pressure, for example, age, for example. Okay. Okay, still okay, still acceptable, right? So even though in the correlation matrix, it indicates high collinearity, but in the collinearity statistics, it is still acceptable, right? So you need to decide, the researcher need to decide whether to retain the variables or to remove the variables based on suspected multicollinearity from the correlation matrix. Okay? Okay, so the next step, is to check for interaction. Okay, so interaction term in linear regression, it need to be computed. So you need to calculate the interaction term. Okay, normally using multiplicative method, we multiply the two variables. The interaction term need to be biologically meaningful, right? So if you have only two variables, then it is okay to check the interaction because you have only one interaction term. So, but let's say you have 10 independent variables. So to check all the interaction, all the possible interaction term is takes lots of time lah, right? Yeah, laborious. So you can choose interaction term which you can explain, right? Which you think is meaningful, right? So you don't have to check each of the interaction term, right? And the interaction term is added to the model as an independent variable, one at a time. If there's a significant interaction term, the model should be the main model, effect model with the significant interaction term. It means that the interaction term need to be included in your model, right? Okay, so how to perform the analysis is to compute. The first step is to compute the interaction term between BMI and also resting heart rate. So transform compute variable BMI resting heart rate is equal to, we use multiplicative method, BMI multiply by resting heart rate, then click OK. Okay, so now one additional variable will be generated, which is the interaction term. So what we need to do is to perform linear regression analysis and add the interaction term to our model. Okay, we remove the collinearity diagnostics. Okay, we just want to see whether the interaction term is significant or not in our model. So now we can see that the interaction term between BMI and also resting heart rate, the p-value is more than 0.05. It means that there's no significant interaction between BMI and also resting heart rate. Okay? So if the p-value here is significant, then it means that the BMI and also resting heart rate have significant interaction term, right? So in your equation, you need to include the interaction term as well. Okay? But for interpretation, it is slightly complicated. It is not straightforward compared to model without interaction. Okay? So in your analysis later on, if you have interaction term, you just report there is interaction term. Okay? For interpretation, so you need to seek help from statistician. Okay? So it is not quite straightforward how to interpret interaction term. Okay? Okay, so the next step is to check for assumption. The assumption is more or less similar to assumption of simple linear regression. Right? We have LINE, linearity assumption, assumption of independence, normality assumption, assumption of equal variance, assumption of independent numerical variable linearity. It means that each independent numerical variable have linear relationship with the dependent variable. Okay, and also assumption of interaction. Okay. So how to check assumption of linearity? Remember during our previous lecture on simple linear, you can during simple linear regression analysis, you can check in assumption based on the scatter plot of the original values, okay, of the raw values of independent and also dependent variable. Or you can also check the assumption of linearity based on the scatter plot of residual. Okay, scatter plot of residual. Here, if you plot residual versus predicted values, scatter plot, you can examine the assumption of linearity. Assumption of independence need to be settled during design. Okay, your observation must be independent of each other. Normality of response variable based on histogram and also box plot of residual. Assumption of equal variance based on scatter plot of predicted and also residual value. Independent numerical variable linearity examined by scatter plot of residual versus independent numerical variable. For assumption of interaction, this one we have checked during our previous step, okay, checking interaction and also multi-collinearity. Okay, so note that for multiple linear regression, all these assumption check based on the residual, right? So we call it the residual diagnostics. Okay, so in order to obtain the residual, we must generate the residual. We must create the predicted and also residual values. Okay, so how to get the predicted and residual values? You need to run your model. Okay, so now we remove the interaction term. So under save, click save, choose unstandardized predicted and also unstandardized residual. Then continue and OK. So in your data set, two new variables will be generated. One is predicted values. Another one is residual values. Okay. Okay, so the first one is we generate scatter plot of X predicted and Y residual. Okay, so X predicted and Y residual to check for assumption of overall linearity and assumption of equal variance. Okay, so go to graph, legacy dialog, scatter plot, simple scatter, X predicted, Y residual. Okay. Okay, so based on this plot, you don't want any peculiar shape. Okay, all the dots need to be randomly scattered around the zero line. Okay, no peculiar shape. Then you can say that the assumption of linearity, overall linearity, and also assumption of equal variance fulfilled. Okay. So the next one, you can also straight away perform the check assumption of each independent variable linearity. Okay, again, what is our independent variable? AMI and also resting heart rate. So the first one, BMI. Okay. Okay, so this one even nicer plot. Okay. So you can see that all the dots, all the residuals scattered around the zero line for BMI. So it indicates that BMI have the assumption of linearity, independent variable linearity for body mass index fulfilled, right? So next we perform again another scatter plot for resting heart rate. X is resting heart rate. Okay. Okay, so there's no peculiar shape indicating the assumption of individual variable linearity fulfilled, right? So what else? We can check the assumption of normality based on histogram and also box and whisker plot. Okay, you can use option here, box plot and histogram, or you can straight away use explore function, explore menu. Use the residual. Okay, you can examine the histogram of the residual. Okay, so here it has nice bell-shaped curve indicating normality of the residual, and also you can look at the box and whisker plot, right? So box and whisker plot here also indicates that there's no violation in assumption of normality. So you can look at other plot as well, for example, QQ plot, right? So there's not much deviation from the hypothetical normal line, indicating fulfill the data, the model fulfill the assumption of normality. Okay. So what else? So we have generated the XPYR scatter plot to see the assumption of overall linearity, histogram and box plot of residual to see the assumption of normality of response variable. Okay, XPYR scatter plot to see the assumption of equal variance, X independent, Y residual to look at the assumption of independent variable linearity. Okay, so by looking at all those plots, we have checked all the assumptions for linear regression, multiple linear regression. Okay. Okay, so lastly, we do interpretation, right? So we interpret our model and also we do presentation of result. Okay, so interpretation, there is a significant linear negative relationship between BMI and also VO2 max. Those with 1 unit increase in BMI have 0.77 unit lower VO2 max when adjusted for resting heart rate. Okay. Again, significant linear negative relationship between heart rate and resting heart rate and VO2 max. Those with 1 beats per minute increase in resting heart rate have 0.16 unit lower VO2 max when adjusted for BMI. Okay. So notice that BMI is being adjusted for resting heart rate. Resting heart rate is being adjusted for BMI. Okay, we also interpret the R square. Okay, the R square of the model is 73.1%, indicating that 73.1% of the variation in VO2 max is explained by BMI and resting heart rate according to the multiple linear regression model. Okay, this is how you can present the results in a table. Okay, for some people, they like to separate. They like to make two tables, to present as two tables. One table for simple linear regression, another table for multiple linear regression. Okay, so it's up to you, and also it's up to the, for example, if you are submitting to journals, then you need to look at the journal requirement, how to present tables for simple and also multiple linear regression analysis. Okay. Okay, so any question so far? So this is your final model equation for prediction. So you can predict VO2 max based on BMI and also resting heart rate. Okay, so any question before we go to general linear regression? Any question?
Hello, doctor.
Yeah.
Just want to double confirm the multi-collinearity. What's the threshold for Is it 0.6 or 0.7?
For
When
correlation,
IVs,
from correlation matrix.
when IVs they have correlation between each other. Yeah.
Okay, the value, the cutoff point is actually arbitrary. Okay, there's no clear-cut definition for multicollinearity based on correlation matrix. Okay?
Oh, okay.
So normally it's up to the researcher to determine the cutoff point. Okay, but normally we use 0.7 or 0.6 and above. Okay, so if you want to be more stringent, then you can use 0.6. If you want to be less stringent, then you can use 0.7. Okay?
Okay, doctor.
Why? Because anything beyond 0.5 for correlation, it's actually, you can say that there's strong correlation already, right? So any correlation of 0.5 and above, it can be interpreted as strong correlation, right? Okay, so another thing to note that the interpretation I've mentioned just now is based on the unstandardized beta, okay, unstandardized coefficient. Okay, in unstandardized coefficient, the interpretation is 1 unit increase in the independent variable, how much increase in the dependent variable. For example here, negative 0.77, it means that every 1 unit increase in BMI, VO2 max will reduce by 0.77 unit, right? It is based on unstandardized beta. Some researcher, they report as standardized coefficient. Okay? So you need to be very careful. You need to look at the results from the journals carefully. Identify whether it is unstandardized or standardized coefficient. For standardized coefficient, for example, here, it indicates that, for example, here, negative 0.641. So how to interpret standardized coefficient? For standardized coefficient, what the analysis do is to standardize the independent variable and also the dependent variable. Okay, so interpretation is slightly different. So here, for example, it means that for every 1 standard deviation increase in BMI, the outcome variable, VO2 max, will reduce by 0.6 for 1 standard deviation. Okay, the interpretation is not in the raw measurement anymore. It is in the standard deviation unit. Again, for resting heart rate, if you want to report the standardized coefficient, it means that for every 1 standard deviation increase in resting heart rate, VO2 max will reduce by 0.31 standard deviation. Okay? Some people prefer standardized coefficient. Okay, so this one is for you to read. Okay, what is the difference between unstandardized and also standardized coefficient? Okay, and also the importance of each one of these, standardized and also unstandardized coefficient. Okay. Okay, so lastly is the general linear regression. Okay. General linear regression is an extension of multiple linear regression. Okay. For some people, they still call it multiple linear regression analysis. Okay, but it is actually a general linear regression analysis. The GLR is a multiple linear regression model with one or more categorical variable in the model. Okay. For example, here, you want to predict one numerical variable. Your dependent variable is a numerical variable. You have three independent variables. The first one is numerical. You have three independent variables. One is numerical. The second one is numerical. The third one is categorical. Okay. So by adding at least one categorical variable in your multiple linear regression model, so it automatically become a general linear regression model. Okay. So to perform general linear regression model, there's some requirement need to be fulfilled. For dichotomous variable, the coding must be 0 and 1. Okay, for example, for sex, 0 for female, 1 for male. Okay, 0 is always your reference group. Okay, so when you do coding 0 female, 1 male, in your analysis later on, you are going to compare the influence of male compared to female. Okay, so man is being compared to woman. 0 is the reference category. If you want to do analysis for female compared to male, then the coding need to be 0 for male, 1 for female. Right? For hypertension, for example, 0, no hypertension, 1 with hypertension. Okay? In your analysis, it means that you're comparing patients with hypertension to those without hypertension. Okay? The 0 group, the 0 is the reference group. Okay? So for dichotomous variable, it is not much problem. Okay? So the equation can be written as, for example, if you have one dichotomous variable, your preliminary equation can be written like this. This is not preliminary. This is equation if you have, if the variable, if the beta for sex is 0.61, hypothetical. Okay? So it means that VO2 max equal to all this initial numerical variable plus 0.61 multiplied by male. Okay, if in your model the beta for male is beta for sex is 0.61. Okay, so if the person is male, then it is 0.61 multiplied by 1. Okay, if the person is a female, then it is 0.61 multiplied by 0. Okay, so it means that for female, you need to interpret only the initial part of the equation. Only for male, you need to interpret all these three, 1, 2, and 3 variables equation. Okay. So what if you have more than 3 categories? If you have 3 or more categories, you need to create a dummy variable. Okay, for example, if you have race 0, 1, and 2. For example, in the example data set, race, okay, race is nominal variable, descriptive characteristics, so Malay, Chinese, and Indian. Okay, so you need to come up with with 2, we call it dummy variable, 2 additional variable, with 1 variable as the reference group. Okay, for example, remember just now, male and female, one of the group need to be the reference group, right? So if you have 3 or more groups, similarly, one of the group need to be your reference group. Okay, so for example, if you choose the first group as your reference group, you need to create 2 dummy variables. Okay, one for whether the person is Chinese or not, and the third variable is for whether the person is an Indian or not. Okay, so just create 2 additional variables. One is Chinese, yes or no. One for Indian, yes or no. Okay, so you include these 2 variables in your analysis. Okay, for example, here, so include the 2 variables in your analysis, and to indicate that the first variable, the first group, Malay group, is the reference group. Okay, for example, here, okay, So this one for Chinese compared to Malay. This one Indian compared to Malay. Okay. Okay, so if both variables are significant, for example, this is hypothetical result, right? So you include these two variables in your model, right? This is just hypothetical, not from this analysis. Okay. From this analysis, both groups compared to Malay, not significant. Okay, so that's all. Thank you. Any other question? Any question before we end our class? So I will provide to you the data set and you can do hands-on practice on your own. Okay. And if you like to learn how to use other software, for example, R, to perform linear regression, you can go to the internet and search for tutorials to perform analysis using R. But basically, the analysis, the theories of analysis is from this lecture note as well. Okay, any question?
No, Doctor.
No, Doctor.
Okay, yeah. Still digesting. Okay. Hari ni kelas daripada pagi sampai malam Since 9 a.m. Hat-trick lah. Very tepu already. Jaga-jagalah, jangan duduk bawah sprinkler lah. Kalau ada sprinkler pemadam api kat atas tu, jauh-jauh sikit lah. Panas sangat nanti kan. Tomorrow pun sama. Okay lah. Okay, so never mind. So you can look back at my lecture note and you can do hands-on on your own. If you have any question, you can always contact me through WhatsApp or through email. Okay? Okay. So I think that's all. Thank you very much.
Thank you, Doctor.
Okay, thank you.
Thank you, Doctor.
Thank you, Doctor.